In the previous video, we looked at definitions for simple and closed curves and simple and connected regions. And then we used this to talk about different types of vector fields and to discover the fundamental theorem for line integrals. There are two basic questions remaining. The first is, how do we determine if a vector field is conservative so that we know we can use the fundamental theorem for vector line integrals? And the second is, if we do know it's conservative, how do we find that potential function so that we can use the fundamental theorem for vector line integrals? Let me share my screen with you, and we'll get started on the next part. We're going to start with, how do we know that a vector field is conservative? To determine if a vector field is conservative, recall from previous section that if it is conservative, it does have the cross-partial property. Now, that doesn't prove it's conservative, but if it doesn't have the property, then it's not conservative. Our question is going to become, are there conditions under which we can use the cross-partial property to prove that the vector field is in fact conservative? And the answer to that question is yes. Let's go ahead and review what the cross-partial property of conservative vector field says. First, we allow F to be a vector field in either 2 or 3 dimensions, such that the components of the vector field have continuous second-order mixed partial derivatives on the domain of the vector field. If we let our vector field be P, Q in R2, then the cross-partial property tells us that the partial of P with respect to Y is equal to the partial of Q with respect to X. P is the first component in the I hat position, and Q is the component in the second place in the J hat position. So we're taking the cross partials, the partial of P with respect to Y and the partial of Q with respect to X. If it is conservative, then those are equal. If we define it in 3 dimensions as P, Q, and R, where P, Q, and R are themselves scalar valued functions of X, Y, and Z, and we know that the vector field is conservative, then we have the cross-partial property in 3 dimensions. In order to do this one, it is somewhat simpler to write it in a circular pattern and then to apply it in a circle. So we have P, Q, and R. Remember that P is in the X or I hat position, and Q is in the Y or J hat position, and R is in the Z or K hat position. Then we do the cross partials, moving around in a circle in both directions. If we're looking at these, then what we have is that the partial of P with respect to Y has to equal the partial of Q with respect to X. That's the first one you see here. You can also write it in the partial derivative notation, P sub Y equals Q sub X. Then we want to know if the partial of Q with respect to Z equals the partial of R with respect to Y. That is the second one you see here, and that gives you the partial of Q or Q sub Z equal to R sub Y. Finally, our last one tells us that the partial of R with respect to X equals the partial of P with respect to Z, or P sub Z equals R sub X. If it is a conservative vector field, then it definitely does have this property. Just because it has the property does not prove it's conservative, but there is a condition under which it does prove that it's conservative. Let's see when this happens. If the domain for the vector field is open and simply connected, then we know that having the cross-partial property gives us that it is a conservative vector field. So we've had in the past that if it was a continuous vector field on an open connected region and path independent, then it had to be conservative. Now we have another rule that says if it is on an open, simply connected region and it passes the cross-partial property, then it is conservative. This gives us another summary fact to add to our list of summary facts about conservative fields. Here's the theorem statement. If the vector field F equal to PQR is a vector field on an open, simply connected region D, and it exhibits the cross-partial property throughout that domain, then it is a conservative vector field. We have the same theorem, of course, in 2 dimensions as well. If the vector field F is equal to PQ on an open, simply connected domain, then, and we have the cross-partial property, then we know that it's conservative. Note that both of these require 4 conditions to be met. The first one was continuous vector field, open, connected region, and path independent. This one now gives us that we have an open, simple connected region and the cross-partial property, then it's conservative. We have several different ways of showing that a vector field is conservative. Proving this theorem is well behind us at this point, so you're just going to have to take this one on faith. Let's go ahead and take a look at how we will use this cross-partial property. If we know that the vector field is defined on the open, simply connected region, then all we have to do to prove that it's conservative is show that it has the cross-partial property. And these become an if and only if. Given that it's a vector field on an open, simply connected region, then if F exhibits the cross-partial property, it will happen if and only if it's conservative. And this can be said in either order. Remember that if and only if statements are bidirectional implications. You can swap each part and it's still true. In order to do this, remember that both R2 and R3, the real plane and the 3-dimensional space we live in, are both open regions and simple and connected. You can get from any point in R2 to any other point in R2 without leaving R2. R2 does not have any holes in it, so it's also simple and open because it goes from -infinity to infinity along both dimensions. In 3D, we have the same situation. In 3 dimensions, we have 3 dimensions going from -infinity to infinity, which makes it open. It's simple because there's no hole that powers all the way through R3, no wormhole, if you like, and it is connected. I can get from any point in R3 to any other point in R3 without leaving R3. Let's look at example 5. We have a vector field given by sine of x cosine y, comma cosine x sine y, and we want to decide whether or not it's conservative. The first thing we need to do is figure out what the domain is. What region is it defined on? Since sine of x and cosine of y, cosine of x and sine of y are defined on all real values, then it's defined on all of R2. Because it's defined on R2, I know that R2 is open, simple, and connected, which gives me my first 3 conditions. Then I simply need to show that it has the cross-partial property, and that will prove that it's conservative. Pause the video now to find the cross-partial and determine whether or not it's conservative. Note that P as a function of x and y is sine x cosine y. I want to find the partial of P with respect to y, the cross-partial. The partial of P with respect to y is negative sine x sine of y. Q is the second component of the vector field, cosine x sine of y. I want to find the cross-partial, the partial derivative of q with respect to x, which also gives me negative sine x sine of y. Because these are equal, and because it is an open, simple, and connected region, then I know that meeting all four conditions means that it is, in fact, a conservative vector field. Then I could find a potential function, and I could use the fundamental theorem for vector line integrals to compute the integral of f dot dr over a curve, rather than using f of r of t dot r prime of t. That brings us to our next question, which is, how do we find the potential function if we know that the vector field is conservative? So in this part of the notes, we're going to assume that all of our vector fields are conservative, and we're going to find the potential function f such that del of f is equal to the vector field. In other words, we're trying to prove that the vector field PQ or PQR is equal to the partial of the potential function with respect to x plus the partial of the potential function with respect to y plus the partial of the potential function with respect to z. Let's now go ahead and equate the components of this equation. If this is true, then P must be the partial of the potential with respect to x, and Q must be the partial of the potential function with respect to y. If it were three-dimensional, then the partial of the potential function with respect to z would equal to r. We'll work an example in 3 dimensions after we've gotten down the 2-dimensional case. If this is the case, then I can integrate both sides of the first equation with respect to x in order to get a candidate for the potential function f. When I do this, I'm taking the integral of p with respect to x, since that's what's on the right-hand side. When I do this, I'm only integrating with respect to x. So my constant term, or what normally is plus c, could in fact be a function that depends on y as well as a constant. If I were to integrate the second partial derivative, the partial of the potential function with respect to y equal to q, I would be integrating the right side q with respect to the differential dy. Since I'm integrating only with respect to y, my constant term that I add at the end of an indefinite integral could in fact be a function of x along with a constant value. Remember, when you're integrating with respect to x, anything that is a function of y is considered a constant. And when you're integrating with respect to y, any function with x only is considered a constant. These become our plus c's. You really only need to compute one of the integrals or the other. You start with the definition of the gradient of f, that the partial of f with respect to x is p, and then integrate both sides with respect to x, or that the partial of f with respect to y equals q, and integrate both sides with respect to y. When you do this, you're going to get a value. We only need to work one of these, and typically most students prefer the integration with respect to x, but if it looks like the other integral is easier, then you should definitely use the other integral. I just noticed a typo in my notes, so make sure that you have that this should be the partial of f with respect to y times the differential dy. Let's go ahead and think about what would happen if we integrated the one on the left, the partial of f with respect to x. If we integrate p with respect to x, we're going to get some function of x and y plus possibly a function of just y, along with possibly a constant value like 5 or 2 or e. Once we have this, this becomes our candidate for the potential function f. F will be this g of xy plus h of y, where h of y may include the constant. Now we're going to take the partial derivative of this candidate with respect to y. We're going to use the one partial derivative we haven't used yet. By definition, the partial of f with respect to y is q. But if we take the partial derivative of g of xy plus h of y with respect to y, we get the partial derivative of g with respect to y plus h prime of y, since h is a function of only y. Once we have that, we set it equal to q, and we can solve the equation for h prime of y. When we solve for h prime of y, we can then integrate with respect to y to find h of y. Once we have h of y, we return to our candidate for the potential function and replace h of y in the expression for f. This will give us the value of the potential function f of x and y as g of x and y plus h of y plus possibly a constant. Probably the best way to learn this, of course, is simply to do an example. Let's go ahead and work an example together, and then we'll work several separately so that you can get the hang of this method. In example 6, we're told that the vector field F is a conservative vector field. We want to find the potential function lowercase f of x and y, such that del of lowercase f equals the vector field uppercase letter f. The vector field is given by y e to the x plus sine y for the first component, and e to the x plus x cosine of y for the second component. We need to decide which will be easier to compute. The partial derivative of f with respect to x dx, in other words, the integral of p dx, and since p is the first component, y e to the x plus sine y, then we would be integrating that with respect to x. Or if it would be easier to integrate the partial of f with respect to y times, oops, and I've got another typo, I'll have to fix that one, should be dy, which is equal to q dy. Q is e to the x plus x cosine of y. Which of these two do you think would be simpler or easier to integrate, if either? If it doesn't matter, most students will choose the one where you integrate with respect to x. I don't really know that one is easier than the other, but at least if I integrate with respect to x, then I don't have to deal with the trig function. So I'm going to go ahead and choose to integrate p dx. When I do this, note that I have to integrate y e to the x, but y is considered a constant since I'm integrating with respect to x. So I just get y e to the x since the integral of an exponential is the exponential. Sine of y is considered a constant as far as x is concerned. So I get x sine of y. Plus, I possibly would get some function of y, which I simply add as h of y. I don't know what it is, but it's possible that I have a constant which represents a function of y, possibly also including constant values. Once I have this, this becomes my potential function candidate, f. Y e to the x plus x sine of y plus some unknown function h of y. I also know that the partial derivative of f with respect to y equals q. I haven't used that yet, so now I use this applied to my candidate for f in order to find the value of h of y. The partial of that potential function with respect to y gives me e to the x plus x cosine of y and plus y h prime of y. I set that equal to q. This part that you see here is the partial of f with respect to y, where f is this function. The right-hand side is the evaluation of q from the original definition of the vector field. Once I have this, notice that I've got two terms on both sides of the equation that are identical. The exponentials will cancel one another, and the x cosine of y's will cancel one another. This tells me that h prime of y has to be 0. Now I would integrate h prime of y to get h of y. But what function do you know whose derivative will give you 0? Yes, that's right. It has to be a constant. So h of y equals a constant. Now I'm going to rewrite my f, which is y e to the x plus x sine of y plus h of y, with h of y replaced with a constant. If I want to, I can double check that this does give me the vector field when I apply the del operator to it. Del of lowercase f, is that equal to the vector field uppercase F? If we verify, we see that in fact, it is equal to the vector field. Let's go ahead now and take a look at example 7. In example 7, we are again told that F is a conservative vector field, and we're given the representation of it. It's a two-dimensional vector field, so we have P, e to the x y cubed plus y, and Q, 3 e to the x y squared plus x. And we want to find a potential function, lowercase f, such that del of f, the gradient of f, is equal to the vector field. Go ahead and evaluate now, then turn the video back on and we'll work it together. In order to find the potential function, we need to determine which integral is easier to calculate, the integral of p dx or the integral of q dy. When we're looking at this, remember that what we're stating is that the partial of f with respect to x is p, and the partial of f with respect to y is q. Looking at these two, one's not really easier than the other, although if I integrate q with respect to y, I'm going to get y cubed divided by 3. But because I have a 3 constant factor, the 3's cancel. So I wouldn't say that that's more difficult than integrating p with respect to x. However, most people have a bias towards integrating with respect to x, so we'll go ahead and do that here. Would you get the same value if you instead chose the other? The answer is yes, you would. When we integrate p with respect to x, we get our candidate function for the potential function lowercase f of x and y. It's e to the xy cubed plus xy plus some unknown function of y. Remember that if we were to undo this by taking the derivative with respect to x, the derivative of some function of y would simply be 0 and it would be gone, and we would get back to the original integrand. Now that we have our candidate function, we want to use one of the partials that we haven't used yet. In this case, there's only one other, which is that the partial of f with respect to y is q, the second component of the vector field. In order to solve and find h of y, we need to take the partial of our candidate function with respect to y and set it equal to q. Q is 3 e to the xy squared plus x, and when we take the partial with respect to y only of our potential function, we get 3 e to the xy squared plus x plus the derivative of h with respect to y. Notice the last one is a true derivative because it's only a function of y, so it is a straight letter d, not the curved partial. Because we have two terms in common on both the left and the right side, they cancel, which again tells us that h prime of y equals 0. While this doesn't happen all the time, it does happen fairly frequently. If we integrate h prime of y with respect to y, and I need to add my dy, I'll get h of y. When you integrate 0, you get a constant, since the derivative of the constant is 0. Then we put it back together in our candidate function, replacing h of y with c. This gives us the potential function e to the xy cubed plus xy plus a constant. You can always take del of the potential function to verify that it does give you the vector field. We knew that it was conservative to start, and we used this process of multiple integrations to find the potential function. Let's go ahead and rework example 7, but this time let's start by using the right-hand side and integrating q with respect to y first. Go ahead and pause the video to work it out and be sure that you come up with the same potential function. This time we were told to start and use the partial of f with respect to y equal to q. In that case, we can find the potential function by integrating both sides with respect to y. This gives me the integral of q dy, or the integral of 3 e to the xy squared plus x with respect to y. Integrating y squared gives me y cubed over 3. The 3's will cancel. And integrating x, which as far as y is concerned is a constant, gives me xy. I could also have had a function of x, which becomes my constant term. This gives me my candidate for the potential function, e to the xy cubed plus xy plus some unknown function of x. Now I need to use the partial differential that I haven't used yet, namely that the partial of f with respect to x will give me p. To use this, I'm going to take the partial with respect to x of my candidate for the potential function. This gives me e to the xy cubed, since the derivative of e to the x is still e to the x, and plus y, since the derivative of xy with respect to x is y, and h prime of x, since h is a function of only x, it becomes a regular derivative. Then I set this equal to p, which is e to the xy cubed plus y. Notice that I have the same terms on both sides again, so h prime of x equals 0. Then I integrate h prime with respect to x, since it's a function of only x, and this gives me that it could be a constant. Finally, I replace h of x in my candidate for the potential function to get the potential function e to the xy cubed plus xy plus the constant c. This gives me the same result as I got previously. It doesn't matter which you use, but it may be that in some cases one is easier than the other. My advice is to use the easiest one first. We've done several examples of finding a potential function in 2D, but how does it change when you're finding a potential function in 3D? In 3D, we have that del of f is equal to the partial of f with respect to x in the I hat direction, plus the partial of f with respect to y in the j hat direction, plus the partial of f with respect to z in the k hat direction. In other words, this is p plus q plus r, each in the I hat, j hat, and k hat directions respectively. In other words, it's just the vector field f. This gives us three partial derivatives. The partial of f with respect to x is p. The partial of f with respect to y is q, as we saw in the two-dimensional case. But now we have a third. The partial of f with respect to z is r. This is going to give us three possible integrals that we can start with. The integral of p dx, q dy, oops, and I've got another typo I'll have to fix, and r dz. Now that I've got the typos fixed, how do you know which one to use? Again, it's a matter of personal preference. Use the easiest one to use, or the easiest for you. Notice, however, that in this case, when I integrate p with respect to x, my constant term could be a function of both y and or z, which might also include constants as well. When I integrate q with respect to y, my constant function becomes h as a function of x and z. And when I integrate r with respect to z, h is a function of x and y, since those would be considered constants with respect to z. Once we've determined one, then we will find the potential function by setting it equal to that g of x, y, and z plus h of whatever. In this case, let's suppose we use the first integral again, p with respect to x. This will give us g of x, y, and z plus some constant valued function with respect to x of y and z. When we do this, we then need to use one of the two partial derivatives we haven't used yet, either that the partial of f with respect to y is q, or that the partial of f with respect to z is r. When I do that, I will then be able to set up an equation by taking the partial derivative of my candidate function and setting it equal to either q or r. This will give me an opportunity to identify h, the partial of h, with respect to one of the variables. Then I'll be able to integrate it in order to find it. Once I get to there, I'll have a function in terms of only z if I did the second one second. In this case, then I would have a function of only g of z, and I would use the last partial of f with respect to z equal to r to find g prime of z. And I would integrate that with respect to z and put it all together. In other words, it's the same process, but it has to be done multiple times because you have 3 dimensions instead of 2. Let's take a look at an example of this together. In example 9, we're told that f is a conservative vector field, and we're asked to find the potential function for it, where our vector field is given by 12x squared for the first component, cosine y cosine z for the second component, and 1 minus sine y sine z for the third component. This gives us 3 different differential equations. The partial of f with respect to x is p, which is 12x squared. The partial of f with respect to y is q, which is cosine y cosine z. And the partial of f with respect to z is r, which is 1 minus sine y sine z. We're going to determine which of these we think would be the easiest to integrate. I would integrate 12x squared with respect to x, cosine y cosine z with respect to y, and 1 minus sine y sine z with respect to z. Since I want to avoid the trig, I'm going to choose the first. If I'm going to integrate, then I need to go ahead and evaluate p with respect to x. Go ahead and pause the video to work it out, then turn it back on once you've got your candidate potential function. When I integrate p with respect to x, I end up with 4x squared plus some unknown function of the other 2 variables, y and z. Now, in this case, we want to use one of the 2 differentials we haven't used yet. Normally, I would look at this and evaluate which partial derivative would be the easiest to take. In this case, the 4x squared actually only depends on x and not on y or z, so it's equally easy to apply the partial with respect to y or the partial with respect to z. Choose one and go ahead and evaluate it now. Since I've decided to integrate with respect to p first, with respect to x, p dx, then I get 4x squared plus h as a function of y and z, the 2 variables that were not in the differential. Then I need to use either the partial of f with respect to y equal q or the partial of f with respect to z equal to r in order to get a handle on what h of y and z is. In this case, it doesn't matter which one you choose because they're both equally as easy. I've gone ahead and done it with respect to both variables and color-coded it so that you can follow along. Let's do the one in pink first, integrating and using with respect to x first, and then using the partial with respect to y equal to q second. If I write this, then this tells me that the partial of h with respect to y, or the partial of f with respect to y, since it equals q, is going to give me cosine y cosine z. And it looks like I've got a typo here as well. Sorry about that. I'm typo heavy today. All right. So I'm going to take the partial of my potential function, which is 4x squared plus h of y and z, and I'm going to take the partial with respect to y and set it equal to q. Because 4x squared doesn't depend on y, its derivative is going to give me 0. So I just get h of y and z, which is going to be the partial derivative of h with respect to y and z, which is going to set equal to q, which is going to give me the cosine of y cosine of z. Now that I know that the partial of h with respect to y is cosine y cosine z, I can integrate both sides with respect to y to get a handle on another function, g as a function of z. When I integrate, this will give me h as a function of y and z, which is the integral of cosine y cosine z dy. The integral of cosine of y dy gives me sine of y, and cosine of z repeats as a constant factor. I could also have a function of z only as my constant term. Then I rewrite the potential function 4x squared plus h of y and z as 4x squared plus sine y cosine z plus this function g as a function of z. Now I have to use the one I haven't used yet, which is the partial of the potential function with respect to z equal to r. When I take the partial of the rewritten potential function with respect to z, the partial of 4x squared goes to 0. The partial of sine y cosine z with respect to z gives me negative sine y sine of z, as you see here. And the partial of g as a function of z with respect to z is just the first derivative of g with respect to z. Then I set this equal to r. Notice that I do have a like term on both sides, the negative sine y sine z, so they cancel. However, this time I'm left with g prime of z equal to 1. So I integrate both sides with respect to z to get that g of z is equal to z plus c. Finally, I replace g of z and rewrite the potential function as 4x squared plus sine y cosine z plus z plus the constant. Let's repeat the process, but instead of using the partial of f with respect to y second, let's use the partial of f with respect to z second. In this case, if I take the partial of this equation in blue with respect to z, I get the first term dropping out since 4x squared doesn't depend on z, and I get the partial of h with respect to z equal to r, which is 1 minus sine y sine z. In order to find a representation for h as a function of y and z, I differentiate both sides with respect to z, and this will give me h as a function of y and z equal to z plus sine y cosine z, since the integral of negative sine z is a positive cosine z, and sine y repeats as a constant factor. My constant term is a function of the variable that hasn't been used yet, g as a function of y. Then I rewrite my potential function as 4x squared plus h of y and z, which is now z plus sine y cosine z plus g of y. Now I need to locate what g of y is. There's one differential I haven't used yet, which is the partial of f with respect to y equal to q. So I take the partial derivative of my new candidate for the potential function with respect to y. The partial of the first two terms drops out since the first depends only on x and the second only on z. The partial of the third term is going to give me cosine y cosine z, and the derivative of g with respect to y gives me g prime of y. Then I set this equal to q, which is cosine y cosine z. Notice that these terms are alike, and so they cancel out, telling me that g prime of y is equal to 0, so g of y must be a constant. And again, I replace g of y with the constant, and I get this same potential function. If I had started this by using the partial with respect to y first, instead of the partial with respect to x, I would still have come up with exactly the same potential function. Let's go ahead now and start putting it all together with what we learned in section 6.2 and what we've now learned in section 6.3 about conservative vector fields. If we are asked to integrate a vector line integral of the form f dot dr over some curve C, our first question should be, is it a conservative vector field? To ask if it's conservative, we first check to see if the domain is open and simply connected. Most times our domains will be, since most of the time they'll be either R2 or R3. If the domain is open and simply connected, we have 3 of the 4 conditions to prove that it's conservative. The last remaining one is, does it satisfy the cross-partial property of conservative vector fields? This means that the partial of p with respect to y equals the partial of q with respect to x for 2-dimensional, and that the partial of p with respect to y equals the partial of q with respect to x, partial of p with respect to z equals the partial of r with respect to x, and the partial of q with respect to z equals the partial of r with respect to y for 3 dimensions. If the answer to that is yes, then we know it's conservative. If it's conservative, then we're going to go ahead and find a potential function and then use the fundamental theorem for line integrals to calculate the integral. On the other hand, if it does not satisfy the cross-partial property, then it is not a conservative vector field. If it's not conservative, then we're going to parameterize the curve and use the integral f of r of t dot r prime of t dt to find it directly. If it's not an open, simply connected domain, then we also cannot use the cross-partial property. So again, we simply parameterize the curve C and use the integral f of r of t dot r prime of t dt from t equal a to b to find it directly. Let's take a look at our last 2 examples. In example 10, we're asked to determine whether a vector field given by sine x sine y, comma 5 minus cosine x cosine y is a conservative vector field. In this case, the first question we ask is, what is the domain? The domain, since it's sine x, sine y, cosine x, cosine y, is basically any value in the R2 plane, in the XY plane. Since we know that R2 is open, simple, and connected, then we have our first 3 conditions. The question now is, do we have the 4th? Does it satisfy the cross-partial property of conservative vector fields? Is the partial of p with respect to y equal to the partial of q with respect to x? Go ahead and pause the video to compute it, and determine whether or not it is a conservative vector field. In this case, we take the partial of p with respect to y and find that the partial of sine x sine y becomes sine x cosine y. And we take the partial of q with respect to x, and this gives us the partial of 5 minus cosine x cosine y, which is also sine x cosine y. Because the two cross partials are equivalent, along with the fact that it is in an open, simply connected domain, tells us that it is a conservative vector field. Now that we know that it's a conservative vector field, we want to go ahead and calculate f dot dr, by this time using the fundamental theorem of line integrals. We want to find the potential function and then evaluate the potential function at r of b minus the potential function at r of a to compute the vector line integral. In this case, our curve is a semicircle starting at 0 pi and ending at 0 negative pi. This means the radius of our circle must be pi, and we're extending from pi over 2 around to 3 pi over 2. Let your parameterization then be equal to pi cosine t, pi sine of t, for pi between pi over 2 and 3 pi over 2. You'll need this at the very end to apply the fundamental theorem for vector line integrals. Go ahead now and find the potential function and then evaluate using the potential function at the endpoints. Then turn the video back on and we'll look at this together. In this case, we need to go ahead and find the potential function. And since we've already established that it's a conservative vector field, in this case, I looked at the integral of p dx and the integral of q dy, and I decided that p dx was slightly easier. And so in this case, I integrate p dx to get a potential function, f of x and y, which gives me negative cosine x sine y plus some unknown function of y. Then I use the differential I haven't used yet, that the partial of f with respect to y is q, and I take the partial derivative with respect to y of my new potential function, negative cosine x sine y plus h of y, to get negative cosine x cosine y plus h prime of y, and I set it equal to q, which is 5 minus cosine x cosine y. The minus cosine x cosine y's match, and I get that h prime of y must be 5. Since h is a function of y, if I take the integral with respect to y, I find that h of y is equal to 5y plus a constant. Now I rewrite my potential function again, starting with negative cosine x sine y and replacing h of y with plus 5y plus c. Now that I have this, I can use the fundamental theorem for line integrals to evaluate the vector line integral f dot dr. In order to integrate that, I want to find the potential function at the endpoint and subtract from it the potential function at the beginning point. Remember that the vector line integral f dot dr is always equal to f of r of t dot r prime of t dt from t equal a to b. But if it is also conservative, we can go straight to the end and say it's the potential function at r of b minus the potential function at r of a. To parameterize this semicircle, I wrote r of t as pi cosine t pi sine of t, where t varies from pi over 2 around to 3 pi over 2. That makes a pi over 2 and b 3 pi over 2. Then I evaluated r of b by substituting 3 pi over 2 into r to get the vector 0, negative pi. Then I substitute a pi over 2 into r to get the vector 0 pi for r of a. finally, I need to substitute these values in place of x and y in the representation for my potential function. My potential function is negative cosine x sine y plus 5y plus c. I now need to evaluate f of r of b minus f of r of a, where r of b is 0, negative pi, and r of a is 0, pi. When I substitute these in place of x and y and simplify, I end up with negative 10 pi for the final value of the vector line integral. Now, in theory, this problem can also be done by parameterizing, as we've done here, finding f of r of t and dotting it with r prime of t dt. I'll tell you right now that I tried this on my own and got about a third of the way into it when I realized that the integral was super difficult to compute. It would probably require the sum and difference of trig functions in order to evaluate. So while in theory it can be done, if in practice, if it's conservative, it is probably easier to find the potential function and evaluate f of b minus, or f of r of b minus f of r of a. This is the end of the section for 6.3, where we were talking about conservative vector fields and their relationship to vector line integrals. In the next video, we'll be taking a look at what's called Green's theorem, which applies in the two-dimensional case. Green's theorem is one of the fundamental theorems of calculus, and it's very important in the later sections of this chapter. See you soon.